Okay, so let's now write down the result after we have used these two delta functions. So we will have, the first thing I'll do is write this integral, d4p1 over 2 pi to the 4, together with this exponential. E to the minus I will have p1, and p5 must be replaced by p1 because of the delta, and we'll have x1 minus x2. The reason why I want to do that is that now everything else, everything in the square bracket, this will be the Fourier transform of this Feynman diagram. So we will have minus 4 factorial I g z squared. This will be squared, and it will be over 3 factorial. Then we still have the integral over p2. So there'll be a d4p2, d4p2 over 2 pi to the 4. And we've also got an integral over p3. So d4p3 over 2 pi to the 4. We don't have the integral over p4 and p5 because we've used the delta function to do those. And now we will have all of the propagators. So we'll have an I z inverse p1 squared minus m squared plus I epsilon. We'll have an I z inverse p2 squared minus m squared plus I epsilon. We'll have an I z inverse p3 squared minus m squared plus I epsilon. We'll have an I z inverse, and then for p4, we should use the result after we have used the delta function to replace p4 by p1 minus p2 minus p3, and then minus m squared plus I epsilon. You've got one more propagator, and here we should replace p5 by p1, again because of the delta function. So that's the answer after integrating over the two deltas. And you can see it looks nice and simple, okay? So now we're just going to quote the Feynman rules in momentum space. In momentum space, okay? And I'm really only going to list the differences between position and momentum space. So as a first step, you'll draw the diagram, okay? So this is the diagram that we're looking at. So you just draw the diagram. Then you assign momenta to each line in a way that P mu is conserved at each vertex. So we'd start off, well, we can give this line over here P1. We can give that line over there P2. We can give this line over here P3. But now we're not free to specify the last momentum at this vertex. That follows by energy momentum conservation. And what you can see is we've got P1 flowing in, P2 flowing out, P3 flowing out. So flowing out over here has to be P1 minus P2 minus P3. And over here, we're not free to choose this momentum. This is the last momentum around the vertex, so we can't choose it. So what is that momentum going to be equal to? Well, P1 minus P2 minus P3 flows in, P3 flows in, and P2 flows in. So the sum of those must flow out. So P1 must flow out. Good. So now we've assigned the momenta consistent with momentum conservation at each vertex. And now let me just introduce a little bit of language. So we have external momenta. Now, these are the momenta associated with external lines. So lines that connect to dots. For this Feynman diagram, the external momenta are the two P1s. Those are the momenta for the two external lines. We've also got internal momenta. Internal momenta are the ones that momenta on lines that do not connect to dots. So P2 and P3 would be internal momenta. This last momentum, P1 minus P2 minus P3, it is an internal momentum, but it's not independent of the momenta that we've written down so far. Then, for each line, for line of momentum, P nu, you get I Z inverse P squared minus M squared plus I epsilon. You need to integrate over the internal momenta. So for this Feynman diagram, we'd be integrating over P2 and P3, and that's exactly what you see in the square bracket. We integrate over P2 and P3. So you integrate over internal momenta. For the vertex, there is no longer an integral over the position of the vertex. So the vertex is now just replaced by minus I 4 factorial G Z squared. And then finally, the symmetry factors are as before. So 1/2 for closed lines, 1 over Q factorial for Q equivalent vertices, or for Q equivalent lines, or for Q equivalent diagrams. So you calculate those exactly as you have been calculating those previously. And that then gives you the Feynman rules in momentum space. Now, that expression in the square bracket is a very specific form. You've got some integrals over momenta, and you've got some I over IZ inverses over P squared minus M squared plus I epsilon type factors. To actually evaluate the Feynman diagram, you'd need to do that integral. And because that integral has such a specific form, there are actually methods that have been developed to do these integrals, and we will be discussing those soon. So you'll actually be able to evaluate these integrals in momentum space. And in quantum field theory, it is most of the time you actually work in momentum space. Good. So that completes our discussion of the Feynman rules in momentum space. You can write down the expression for any position space Feynman diagram. Why don't you pick another Feynman diagram, write down the position space expression for that Feynman diagram, do the Fourier transform, see what you get, and check that you can reproduce your Fourier transform using the rules that we've written down here. That would be a very good exercise to check that you've understood the Feynman rules in momentum space. Good, we'll discuss the exercises.